Hello everyone, welcome back. Last time we started looking at the magnetic field and how that created forces on charges. Let's remember what we did. Let's imagine we've got some charge Q, and let's assume it's a positive charge for the moment, that's moving at some velocity v, that is in a magnetic field, and let's assume the magnetic field is in some direction like this, so that there's an angle of theta between the velocity vector and the magnetic field. We know then that there is a force acting on the charge. The magnitude of that force is given by the magnitude of Q times the magnitude of the velocity times the magnitude of the magnetic field, QVB, times sine of theta. Let's remember, what is theta? Theta is the angle between the velocity vector and the magnetic field vector. The angle between V and B. So the angle between V and B, putting the vectors tail to tail, whatever that smallest angle is between them. If the angle becomes, if they're opposite each other, the angle is 180 degrees. But if they start coming back the other way, remember the angle is always measured the smallest angle between them. Theta always has to be less than or equal to 180 degrees, or greater than or equal to 0 degrees. There we go. There's the magnitude of the force. How do we find the direction of the force? What do? We have to use the right-hand rule. We had 3 different applications: V, B, F, V, B, F, or V, B, F. So we can try that. V, B, F, so V, my thumb, B, that way, F would be into the board. So in this case, I get F is into the board. What's the direction that we use, or what's the symbol that we use for into the board? A circle with an X in it. Perhaps I shouldn't use this little arrow here to make it confusing. So the force is into the board. So V, B, F, or V, B, F, my thumb points into the board, or V, B, rotate my fingers from V to B, my thumb points into the board. Those would be the direction, or that is the direction, if we have what? A positive charge. For a negative charge, we would have to reduce those, and we would get a force out of the board. Okay, very, very good. Now, let's think about how do we usually have moving charges? Do we usually have a single charge moving all by itself? Typically, no. Typically, we have currents of charges. So imagine we have a wire like this, and there's a current of charges moving in that wire. What kind of force would it be? What kind of force would this wire experience if we had charges moving and the wire were in a magnetic field? Well, let's take a look at that. Let's imagine that this is our wire, kind of greatly expanded. So here's our wire up here, this thick thing right here. For the sake of simplicity, let's imagine that we've got a whole bunch of charges, all the same charge. So we'll assume they all have a magnitude of Q. And again, for the sake of simplicity, let's assume Q is positive for the time being. Let's imagine that in some length L, so some length of wire L, we have N charges. So we'll assume we have N charges of charge Q within our length of wire L. Let's also imagine that this wire is in a magnetic field, and we will assume that the magnetic field B makes an angle of theta with our wire. So if our charges are going in this direction and they are positive, then the direction of the current is also in that direction. Remember, current is always defined as the direction of motion of positive charges. So we can assume that the direction of the current is the same as the direction of the velocity vector, as long as our charges are positive. The angle then between V and B is the same as the angle between I and B. So we're actually going to change to think about the current as opposed to individual velocity vectors. What is the force on each charge? On each charge, we have a force of Q, and I'm just going to write it as Q because we have assumed that Q is positive for the moment. QVB sine theta. That's the amount of force on one charge. What is the total force on the entire wire? We've got n charges. The force on the entire wire would then be n times the force on one charge. So this would be the force, say, per Q. The force on the wire would be n times Q V B sine theta. Now let's think about what is V. We're assuming this is a velocity V. Let's imagine that it takes some amount of time, delta t. We'll call it delta t, which is the time for a charge to go from one end of the wire all the way to the other end of the wire, a distance L away. Delta t is the time it takes for the charge to move a distance L at a speed v. So we know that v must be distance over time, L over delta t. Let's write this then as nq. V I'm going to write as L over delta t, and then b sine theta. What is this part right here? nq, and I'm going to move the delta t over to this part, delta t, L, b sine theta. nq, that is the total amount of charge in the length of our wire. Delta t, that would be the amount of time that it takes for this last charge over here to make it all the way over to this end. In other words, delta t is the amount of time that it would take for all of these charges to pass by this end point of the wire here. So that's the total amount of charge that goes past the end of the wire in an amount of time, delta t. Well, what's that? A total amount of charge passing a point in a time, delta t? That's how we defined the current. So this quantity right here, nq over delta t, that is just the current in the wire, times L, b sine theta. What do we end up with? We end up with the total force acting on the wire is equal to ILB sine theta, where I is the current in the wire, L is the length of the wire, B is the magnitude of the magnetic field in which the wire is, and theta is, remember our first equation, we had theta was the angle between V and B. Now we can think of theta as the angle between I and B. If Q is positive, the direction of the velocity is the same as the direction of the current. So rather than talking about the velocity of the charges anymore, we'll just talk about the direction of the current. If we have some wire like this and the current is going that way, the wire actually tells us the direction of the current. We just think about what's the direction the wire is in, as long as we know what direction the current is, this way or this way. The angle then between the current and, the angle between the current and the magnetic field is that now the way we'll think about theta. Excellent. One more thing, a little modification here. If we don't know what the length of the wire is, or if we want to just talk about some part of the wire in general, sometimes we take this result, divide both sides by L, just get rid of this part. We divide both sides by L and we get F over L, which is IB sine theta. This tells us the force per length. The force per length. In other words, how many newtons per meter is acting on our wire? 5 newtons per meter, 7 newtons per meter. That tells us the amount of force per length, and then we could always multiply whatever length we want to get the force on that particular length. Excellent. Let's stick some numbers in here. Let's imagine we have a magnetic field pointing in this direction. What's this direction? Think about the symbol into the board. So we have a magnetic field pointing into the board and a current that's pointing up this way. The magnetic field is 5 Tesla. The current is 3 amps. Let's figure out what is the force per unit length on the wire, and then we'll put a length in there and figure out what's the force on that particular length. What do we have? Remember, the force per length is IB sine theta, IB sine theta, which is I is 3 amps, times B, which is 5 Tesla, times sine, what is theta? Remember, theta is the angle between I and B. I is this way, B is this way. What's the angle between them? Well, let me make a little physical demonstration of this. So B is into the board, I is up. What's the angle between them? 90 degrees. So sine of 90. Sine of 90 is 1. What do we get? 15, 3 times 5, 15 amp Tesla. But that is also a force per length, so that is Newton per meter. So we have 15 newtons per meter. What's the direction of the force? I want you to take a second, try the right-hand rule. You can turn off the video if you need, or pause the video for a second. I want you to give it a try. Use the right-hand rule. What's the direction? I will assume you've done that. What is it? Thumb goes in the direction of the current, like the velocity. Thumb is now the current. Fingers are the magnetic field. So I want my thumb pointing up, my fingers pointing into the board. So I have to turn my hand around this way. Keep your hand flat. My palm then points to the left. So the force is to the left in this case. Or I, B, I up, B into the board, thumb points to the right. Or I is up, rotate my fingers down into the board, so up into the board, thumb points to the left. So force to the left. There we go. There's the force. Now let's imagine we've got a small piece of this wire. Let's imagine we've got a small 2 centimeter section. So we've got a length of 2 centimeters. To find the force acting on that, we take the force per length and multiply by the length. So the force will be 15.0 newtons per meter times the length. We need to convert that length to meters if we want to cancel out the units. So we have 0.0200 meters. What do we get? Multiply and we get 0.300 newtons. There we go. Very, very good. So that is the force, 0.300 newtons, that's acting on our little section here, and it's going to be pushed to the left. Excellent. Let's take a look at another example, something a little bit more complicated. I want to imagine that we've got 2 currents in magnetic fields, again, but now let's imagine that they're actually made on, the currents are in some strips of copper. So here's a kind of a thin strip. So we've got a strip of copper here, rather than a round wire or something like that. I want to imagine that both of these have currents going upward. So both of these will have currents in the upward direction. But for one of them, I want to imagine the current is made of positive charges moving upward. Remember, current is defined as the direction of the motion of positive charges. So positive charges going up will mean a current going up. While on the other one, I want to have negative charges moving down. Negative charges moving down move in the direction opposite to the current. So downward moving negative charges would still mean a current going upward. I want to see what the direction of the forces are on these 2 wires. We've got positive charges moving up. Let's use our old force equation for the motion of charges. We've got positive charges moving up. We put our thumb in the direction of the velocity, fingers in the direction of the magnetic field, which is into the board. So we're going to have a force to the left. So the force on these charges will be to the left. What about the negative charges? Well, we've got a velocity going down. Fingers going into the board. My palm points to the right, but it's a negative charge, so that means the force will be to the left also. So again, we get a force to the left. Using our force for the current, because both currents are up, pointing our thumb in the direction of the current, fingers in the direction of the field to the left, that tells us that for both currents up, we get forces to the left. So, of course, we get the same thing. That makes sense. Doesn't matter whether we're talking about positive charges moving up or negative charges moving down. But let's think about what effect this is going to have. Here, we've got positive charges with the force pushing them to the left, which means we're going to end up with positive charges pushed over to the left side of the strip, leaving the right side negatively charged. While in this case, we have negative charges pushed to the left side of the strip, which is going to make the left side of the strip negatively charged, leaving the right side of the strip positively charged. If we were to take a voltmeter and put the voltmeter across the two ends of the strip, the voltmeter would tell us that the left side is at a higher voltage than the right side. For this strip, if we were to put a voltmeter across the ends of this strip, the voltmeter would tell us the right side was at a higher voltage, the left side was at a lower voltage. We would get a very different result testing the voltage across the strip, even though we had the same current. This was actually discovered by Edwin Hall in 1879. And this is called the Hall effect. If we were to do this experiment, and I'll tell you, it's a little bit hard to do. The reason is that the separation of the charges is a fairly small effect, and the measurement of that voltage it's a very small voltage, so it's actually hard to measure. I've tried it because I would love to do it as a demonstration, and I couldn't get it to work, to tell you the truth. So I'm very impressed that Edwin Hall actually managed to do it in 1879. But if we could do it and get a result that was big enough to measure, which do you think we would find? Which result do you think we would find if we actually created a current in some piece of copper? Do you think we would get this result or this result? The one on the left or the one on the right? Which do you think? Well, the fact is we would get this result, the one on the left. Why? Because the currents that we deal with 99.99% of the time are made by the motions of negative charges, motions of electrons. I would probably say even more than 99.99% of the time. The currents that we deal with are electrons moving through conducting wires, not the motion of positive charges, but the motion of negative charges. It's the electrons that are actually doing the moving that cause the currents that we deal with every kind of electrical device, from the video camera that's videoing my right now to the lights that are illuminating me, everything. They're all motions of electrons. Very, very good. Let's try another example.